So hello guys, good day. So I hope you are doing fine. So today I'm going to give you a short overview about what is a Z transform. And for this discussion, we're going to use this book, Digital Control Systems by Anastasia Belloni and Nicholas Meridakis. So I have given you a copy of this one in the first topic that we had. So we can, I have here several books, no? You can also use this one. The Normalized Control Systems Engineering, the 6th edition. Also this one. Oh, no title. Anyway, so we're going to have this one. So in chapter 1 of this book, you can see there is a good discussion about digital control system. So if you are able to read this book, I'm sure you have observed that some of the terms here are highlighted. So these are key terms or important terms that discusses about part of control system. So one of the most important theoretical and practical aspects of automatic control is the system's interconnection through a feedback process. So and generally the concept of feedback such that the system input will always depend on its corresponding output. So this is just introduction of the control system. I'm sure in your feedback control system you have discussed this one. So we'll not dig deeper on this one. So going forward, you'll hear a definition of the term system. It is defined as the physical part of the natural world, where we assume that it comprises a set of components which simultaneously operate in a prescribed manner so as to achieve a certain goal. So as you can see here, we have two types of or a control system can be classified accordingly as analog or digital and hybrid. So this is based on the type of signals used in the control system. So kung continuous time yung signal gigamit, so we consider that as analog. But if the signal uses discrete time, meaning na siya levels, meaning it could be 2 or 3 levels. So discrete siya, different levels. May define mo yung different levels, so we could say it is digital. Or kung both analog and digital gigamit, we consider that one as hybrid. So please read this one, this first chapter. So in our upcoming midterm examination, we're going to make use of this book as one of the references for our theoretical problems, meaning for chapter or part 1 would be the identification. So the topics or some of the problems or questions might be taken from this book. So please take note of that one. So by definition, computers are digital systems, hence all input data streams are in digital form. That is digital signals. So this one. So we have here the description of analog and digital control system. So in this part, it is compared and contrast what is the analog and what is digital control system. So this is an analog automatic control system. So this is the basic feedback control system configuration. So we have here an input, desired input here, then desired output at the right side. So for standard control system, here is the input. Oh, it's happening in my anyway, it's not working. So the left side is the input, the right side is the output, and as you can see here, the arrow is from the left to right, so meaning whatever input you have here, it follows the uh, direction of the arrow from left to right. You should have here a target output, but for feedback you have here a feedback loop, which in this case is a counter. This counter give a feedback signal to your input entering inside a summing junction or comparator. So that is feedback to that is fed to controller, then to the control system. So if your target output is achieved, there will be no more feedback input here. So other controls are generally let's read this one. So here we have digital controllers, and in general discrete time systems are described by the Z transform or by differential equations. The problem of developing digital controllers is strictly related to the construction of a PC program. So in this case, this is a hybrid system that both that uses or exhibits both continuous and discrete dynamic behavior. So its main digital part is the controller, that is a part of the computer. Now in this case, there will be a process called analog to digital conversion and digital to analog conversion. No, this one. So the input here is RT, which is a time domain. So the input here is usually analog. So from an analog converted to digital for the computer to process it. So in this case, the E/D is the analog to digital conversion, then fed to the computer. So as you can see here, we have here RT, which is the time domain, but when it is converted to digital, it becomes A to the K. So K here is a discrete signal, then entering the computer, then output is MK, which is a discrete also. Then the output of the computer is fed to digital to analog conversion or converter, then that is fed to control process. Then the output here is CT, which is a time domain, so which is an analog signal again. Then the feedback is taken back to this loop. Then we have here the error time signal, which is the feedback signal given by a feedback loop. So what does the controller do? So the controller computes the error signal and generates the appropriate input signal to the control process in order to provide the desired output signal. So it is highlighted, so I'm sure I hope that you will not forget this statement. So in summary, there are two fundamental differences between the analog and digital control systems. First, the digital control system or digital system computes output samples and not the continuous signal. Second, the digital controller is described by difference equations. So the differential equations which represent the analog controller must be converted to difference equations. Thereby, the signals received by a digital controller are given in a discrete form, while the digital signals or the signals which enter the control system are continuous. Therefore, the continuous signals of the controlled output and the reference input should be sampled so as to provide the appropriate input of a discrete controller, and then the signal generated by the controller must be converted to being continuous to produce an input for the control system. So this one. So here a computer. So as you can see, the input here is fed directly to the AD adapter or the converter. So the working signal here is a discrete signal. Then from your computer, it passes again to the adapter. Then your feedback here is passes another AD adapter. So still the same type of signal is fed here to the controller. So to ensure communication compatibility between the controlled continuous time system and the discrete controller, it is necessary to connect them through elements which achieve the conversion of digital signals to analog and vice versa. So these elements are interface between the system and the computer and are called respectively as the digital to analog converter and analog to digital converter. So the next part here discusses the sampling, or how does the digital to analog conversion and analog to digital conversion happens. So it starts with the sampling process, then the conversion of analog signals to discrete ones. Then we have also quantization and so on. So please read this one. No. So this one is sampling, quantization, then terms on the advantages of digital control systems and its applications over the analog systems. Then here we have our new topic, the Z transform. So actually you can refer to the so you can use several um, material that I have provided to you. For example, this one. Oh yes, this one. I have provided you this one in the previous material, so I can have can use this as a reference. So I hope that you are able to read this one already. So inverse Z transform, this will be discussed after midterm. So we are going to focus first on the Z transform. Alright. So I have here another, this one is a good also topic now. Oops. Let's see this one. Yes, this one. The Z transform. So we can also use this as reference for Z transform. I'm not sure if I've given you this one, but if not, I will provide this in this discussion. Alright, so let's go back to the book. Yes, this one. So the Z transform. So analog systems are designed and analyzed with the use of Laplace transforms. So if you have done Laplace transform in your feedback control system, so this is what it means, no? In your feedback control system, where we focus on the analog inputs. So in this subject, the digital control system, we're going to analyze systems using a similar technique called the Z transform. So the basic lines of reasoning are the same for both scenarios. So after determining the impulse response of the system, the response for any other input signal can be extracted by simple arithmetic operations. So the behavior and stability of the system can be predicted from the zeros and the pools of the transfer function. So as Laplace transform converts the differential equations into algebraic terms with respect to S, Z transform converts the difference equations into algebraic terms with respect to Z. So as you can see, if you could recall your Laplace transforms from T domain to S domain. Now in our case, for the digital control system, we are going to convert T domain to Z domain, or the Z frequency domain. Now it should be noted that the Z plane, the domain of the Z transform, is organized in a polar form, while the S plane is in Cartesian or Gaussian form. So we have here a diagram later, no, which describes this paragraph. The Z plane is in polar form, while the S plane is in Gaussian form. So from Laplace transform to Z transform, so this is the process of solutions of differential equations using Z transform. So from difference domain, N domain to Z domain, that's Z transform. Then from Z domain to N domain, that's the inverse Z transform. So Z to the negative 1, so that's the inverse of Z transform. So the Laplace transform is an integral-based transform that connects the temporal representation of the signal, that is xt, with respect or with its representation in the S domain, namely xs. The Laplace transform is defined as xs is equal to the integral of your xt times e to the negative st dt, where s is a complex number. So the integral is from negative infinity to positive infinity, if that is a two-sided integration. So negative infinity to positive infinity. But most of the time, we only use the half part of the integration. So we start with 0 to positive infinity. So by substituting s with omega plus g, lambda plus j omega, one is able to reach an alternative form of xs function, which is x lambda omega is equal to the integral of your xt times e to the negative omega t times e to the negative j lambda t times j a to the j omega t dt from negative infinity to positive infinity. So this would result into this one. So because of this equivalent, so we have here real value and an imaginary value j, which is a complex. So this is a complex function. So xt signals analyzed in sine and cosine waves whose width exponentially varies in the time domain according to the relations e to the lambda or lambda t, which each point of the complex is placed determined by the real and imaginary part of its parameters lambda and omega. At every point of this plane, one can calculate complex quantity x lambda omega. So this is on the Laplace, since we are dealing here with e to the t. So as you can see here, the real part is the cosine value. Here is the real part, and the imaginary part is this sine value. So as you can see in the next part, in the next page, we have here the real part, the RE, and we have the imaginary part IM. So based on the above representation of Laplace transform, one can formulate the Z transform, that is the corresponding transformation relation to discrete signals, in 3 steps. Number 1 is the first step is the most obvious. Change the signal from continuous to discrete, that is xt to xn. And of course, integral should be replaced with a sum. So instead of integral sign, we're going to get the summation of a certain system from negative infinity to positive infinity. So if you have an x in terms of lambda and omega, if you are going to get the Z transform, we're going to get the summation of your xt converted to discrete signals xn times e to the negative lambda n times e to the negative j omega n. And despite the fact that xn signals a discrete one, x lambda omega is continuous, since lambda omega variables can take continuous values. So in this case, in the case of the Laplace transform, one could go through any point. So if you are going to read this one, this is a good explanation about the Z transform. So So since e here is exponentiation, so the exponential sign or signal yn e to the negative omega n can be written as yn is equal to r raised to the power of negative n, where apparently the substitution e to the omega or e to the lambda is equal to r has taken place, holding that lambda is equal to the natural logarithm of r. Then it can be noted that in the form yn, which is equal to e to the negative lambda n, yn increases with time when lambda is less than 0. So kung less than 0 na yung mga negative, so negative times negative, that would be a positive term. So e to the positive, so that would be increasing yn. Okay, so when r is less than 1, so it is less than, so a negative raised to the power of a negative, so that would be a positive, so increasing again. So when your lambda here is greater than 0, so when you're positive, so e to the negative n, so the value of your e as lambda increases will also decreases. So do you get me? I hope you are able to solve. So what does this mean? Now for example, you have y and not C. For example, you have yn is equal to e is negative lambda n, and let lambda is 2. For example, that's a 2, no? That will become yn is equal to e to negative 2n. So in this case, this is lambda greater than 0. So we have e to the negative 2 raised to the power of n. So what is e to the negative 2? Where's my calculator? So shift e to the negative 2. So that is 0.135 to the n. So if we have lambda less than 0, for example, we have here yn to e to the positive 2n. Let's say your lambda here is equal to negative 2. So that will become yn plus e to the negative 2n. So this is also negative. So the result here becomes positive. So e to the 2n, so yn is equal to e positive 2 of n. So that will become 7.39. So it states here that if your lambda is less than 0, which is a negative, so your yn increases. So nagkadako siya. Because if we let here as example 0 na siya, 0, so e to the 0 is equal to 1. So if your original value is here, for example, if we have if your original value is e to the negative 0, and this is equal to e to the negative 0, or that's e to the 1, it will become 1. So if your lambda is greater than 0, so 1 is greater than 0.135. But if your lambda is less than 0, which is a negative, so it could be compared 1 to 7.359, so that's be repeating piece. So malagi pa sa battery. So if your yn, or if your lambda is less than 0, so increases, so on. Oops. So malagi pa sabot sa kining so hence we have here x in terms of r. So since we have a polar term na, so we have an r. So here, no, we converted r e to the lambda n into terms of r to the n. So r omega. So r is here is the radius, and omega here is the angle. So if you get the z transform, so you're just getting the summation of your xn times r to the negative n times e to the negative g omega n from negative infinity to positive infinity. Then we substitute the value of r z as r times e to the j omega. So we have this formula: xz is equal to the summation of xn times z negative n from negative infinity to positive infinity. Now this become the z transform formula. Okay, so the z transform equation is a valuable tool for analyzing discrete linear time invariant systems. It provides capabilities for, we have here different applications now. By the way, are you familiar with what is this time linear invariant systems? So if not, we're going to have a short or different discussion about this one. Okay, LTI. So comparison of S-plane and Z-plane. So as stated earlier, so ang S-plane or ang Laplace, it uses the Cartesian plane. So the Cartesian plane or the Cartesian plane has an x-plane, x-axis, no, the real axis, and y-axis, the imaginary axis. Now in z-plane, we have here a real value re, so this is the radius, and we have here the omega, which is the angle of your signal or of your radius from the 0 level, no? So you can diri gikan padong diha kung pilang angle yung i-create, so that's your omega. So the distance from 0 up until this point, so that is the radius of our z transform. So man siyang small letter r, so that's the radius. So may differential nila, no? This plane is orthogonal while z plane is polar. So if you're going to have a z transform that is represented in polar form, no, then itong Laplace is in plane orthogonal. So the resulting geometry arises from the fact that each S number, its position is determined by the relation S is equal to lambda plus j omega. So this is for um, the Laplace or the S-plane. No? Now Z-plane is polar based, so its complex number is determined by its distance r from the region and corresponding to the exponential rate of the reaction, and omega parameter corresponds to the angle of r across the positive horizontal semi-axis. So mo siya, no? So ang angle so that is your omega. Then the length here from this to this, so siya. So mo na yung r. Alright. Oops. So that's the background of a Z transform. So what are the properties? So if you have the control systems by NICE, and going to the discussion of NICE with the Z transform, NICE here presented a good summary summary of Z transform. So this is the Z transform, this is the Laplace transform. Now in your activities you can have this printed, no? Para madali niyo mag-solve ang Z transform. So this is Z transform, no? So muna equivalent function in time domain, di man equivalent sa S transform or the Laplace transform. Then most na equivalent sa Z transform. So in the next table na siya ay Z transform theorems. So kini nga theorems mo na gi-discuss diri sa Z transform properties. So same rin sila. So you can see here na kay linearity na. So napo siya diri. So let's focus here kay simple yung explanation diri, no? Number 1, time shift. So if xz denotes the transform of an xn function, then the corresponding transform of xn minus capital N is given by z to the negative n xz. So unsa gimin ani? So for example na kay xn, let's say let's try to have okay. Very sorry. Okay. What? So let's say you have an xn, no? So here we have an example, for example. Example 1. Oops, this one. 1. xn. Let's say our xn here is mu n. So mu n is a step signal, and this is your 0, 1, 2, and so on. This is one value, and oops, one value. The rest are negative 1, negative 2, they are 0. So 1, 1, 1. So this is the step uh, signal. So say this is, oops, remodeling. Step signal siya. Step signal. As you can see here, the Z transform of a step signal is given as Z over Z minus 1. Sorry, this is not this is N. So, N siya. N. N. Z mu N Z to the negative 1. So what does this state's time shift? So sa time shift, ang gimay niya, if your mu N is shifted, for example, that's shifted with N minus 2, okay? So shifted with N minus 2, so here, our capital N is equal to 2. So if you have N shifted with 2, then the Z transform of your mu N minus 2, is just equal to your X N minus N Z negative N times the Z transform of your original equation. So let's use this one. This states that it's just like multiplying and Z to the negative 2 to your answer Z over Z minus 1, which is the original, this one. This is the original X Z. Okay. So this will become Z negative 2 times Z over Z minus 1. So that will be minus 2 plus minus 2 plus 1, that is Z minus 1 divided by Z minus 1, or that would be 1 over Z times Z minus 1. So the final answer here become 1 over Z squared minus Z. So this would be your answer. So kung gawin niya, kung i-shift na to siya, like this one, this is the original, i-shift na to siya 2, okay, you're just like multiplying the shift to your original Z transform. So may naging battery. Okay, so another example. Let's this white na lang. So this white. Okay, example number 2. Let's have example number 2, no? You have mu n. We all know that mu n, ang Z transform niya is Z over Z minus 1. Okay, so if you have a shift mu n, eraser. example, it has been shifted with n plus 3. Okay, so here your n here is negative 3. If you get the z transform of your mu n plus 3, this is just similar to multiplying z to negative 3 to the z transform z over z minus 1. So you have here z cubed times z over z minus 1. So it becomes z to the 4th over z minus 1. So the z transform therefore of your mu n plus 3 is equal to z over. So this is your final answer. So kining mga properties niya, these are just shortcut, no? If you are going to change your original signal. So you have your linearity. So what is this linearity? Okay, ang linearity sa lahi na sa ni. Sample. Sample number 3. Isa black man. Number 3, huh? 3. For example, you have 5 mu n plus it's not this one. Say an example. Let's have xn is equal to 5 mu n. So what's the z transform? So you getting the z transform here is equal to z of 5 mu n. So you'll know the z transform of mu n, which is z over z minus 1. So if you have here a constant 5, so based on the linearity formula, so you just multiply this with 5. So the answer is 5 z over z minus 1. So nga lang. So very simple, no? So that's linearity. So time reverse. So as you can see here, no? Linearity, if xn be a function, is a linear combination of two functions, x1 and x2, with regions of converge phi 1 and phi 2 respectively. The region converge of xn includes in the intersection of phi 1 intersect phi 2. We have here time reverse. So time reverse. So for ang given sa time reverse that your n value here becomes a negative, or it performs folding. Example, it's example number 4. So xn is equal to, still we're going to have mu n, no? So we'll know that the z transform here is xz z over z minus 1. So if you have a reverse one, so ang xn mo, this becomes mu negative n. So what's the z transform? So based on this time reverse property, so if you have an reverse, no, ang n mo na negative n, ang z mo na mahimpong 1 over z. So to get the z transform of mu negative n, so tanang z dire sa imuhang z transform, imo lang isang substitute with 1 over z. So this would become 1 over z, no? And this also becomes 1 over z minus 1. So as you can see here, we're just going to substitute this with this and this with this. Then you simplify. Simplify natin eh. So this will become 1 over z. Denominator will become 1 minus z over z. So cross multiply, become z over z, 1 minus z. Common, so 1 over 1 minus z. So this is our final answer. So yan lang, very simple lang. Here we have here convolution. So for now, convolution ay sila na i-appeal. Differentiation. So here, reality. Okay, so differentiation, let xz be the transform of xn function with region of convergence phi. Then n xn is equal to negative z dxd over dg with the same region of convergence. Okay, so we have here differentiation in z domain. So for example, you have an xn which is an nxn or n mu n. So we all know that in our previous examples, we all know that the z transform of mu n mu n is equal to z over z minus 1. Okay, so if you have here a value n multiplied to mu n, so to get the z transform of that one, if you're going to make use of this property, is that the z transform of n mu n be z times the first derivative of your xz over the z. So what does this mean? So you just get the first derivative of this one. So since atong multiply ka n pa man, so we're going to get the first derivative of this one, then multiplied by z. So we have here z, then the first derivative of z over z minus 1 with respect to z. So what's this? You can use the quotient rule. So what's the quotient rule? can use quotient rule or you can use the product rule. No? If you want to use the product rule, just need to write this one as z times z minus 1 to the power of 1. What's the product rule? First derivative of z, you have here this here u, so p, so the product rule states that u dv plus v dv. Okay, so if you are going to use this one, you can have u z dv. We have negative 1 times derivative v, so that's negative 1 times derivative v minus 1 negative 2. Okay, plus v. V here is z minus 1 1 times derivative of z, which is 1. So simplify, you can have z times negative z minus 1 negative 2 plus z minus 1 negative 1. If you're going to simplify this one, what's the answer? We have z, we're going to get the z here, we have negative z plus z minus 1 over z minus 1 squared. Ano pa negative 2, 3. Ito pa negative sa kanya. Okay, so ito. So simplify further, this would become z times, so negative z plus z, so negative 1 over z minus 1 squared, or that would be negative z over z minus 1 squared. So this would be our final answer. So negative z over z minus 1 squared. So this is the differentiation in z-domain property. Ayan lang, no? So if you have if you are familiar with the quotient rule, you can use that one. I think it's if this is your u, it should be I think it's I forgot the quotient rule. Divided by v squared. U minus v d. So I just use here the product rule and derive its answer. So I think that's the basic properties of the z transform. So here inverse z transforms, after midterm we're going to have this z transform, inverse z transform. So formula tables, you can have here another formula table. And some examples below. You can solve these examples. So that's it for this topic, and I will be giving you a set of questions for you to answer. We're going to submit this before our midterm exam. So the topic for midterm exam would be from start until z transform. Now, as you can see, for the z transform, we are not going to have the ROC now. We are going to tackle ROC later. So for this time period, we are going to solve z transform without the ROC, or the region of convergence. So that's all. Thank you. And if you have questions, drop a message or in the comment section of our Google Classroom. Thank you and good luck.